All right. Hello, everyone, to another Calcaholic video. Today we're doing MIT Integration B Prep with a Feynman's technique question. So we have the integral from 0 to 1 of x to the 7th plus 2x cubed minus 3 all over ln x. Now, this integral is non-elementary, but non-elementary without the bounds. The bounds make this integral doable. And how do we do it? Well, I've kind of given you the hint in the title. It's using Feynman's technique. And it's a very sophisticated version of Feynman's technique. So let's go ahead and write our integral from 0 to 1, x to the 7th, plus 2x cubed minus 3 over ln x dx. All right, cool. Now, how do we use Feynman's technique? Well, for those of us that don't know, is we have our integral, our target integral, and we want to parameterize it. So let I equal this integral, and then enter a parameter. So we make an integral equation with goals to simplify after differentiation. So I'll show you what I mean by this if you're confused. So notice that I've entered the parameter t into this integral equation. Okay, well, what the hell does this have to do with my previous integral? Well, if you notice, if t is 7, then I have this original integral. So what the goal is to set up a parameter and then differentiate under the integral. So let's go ahead and differentiate both sides. We'll get I prime of t. The derivative of integral of 0 to 1 x to the t plus 2x cubed minus 3 over ln x dx. So we've differentiated both hand sides. Well, what the hell do we do from here? And what I'll tell you is that notice we have no problems with convergence in our integram. So we can actually flip-flop our integral and derivative operator. So let's go ahead and do that. But more importantly, upon flipping, this derivative becomes partial, and that's the key for this change in parameters technique, is that differentiating the integral becomes partial under the integral, which is very important. So now we have I prime of t equals the integral from 0 to 1 of x to the t. And before I continue, just let me make a little kind of indication that this is all constant. And why is it constant? We have x. How the hell is this constant? Well, it's constant because we're differentiating partially with respect to t, and x is not the variable we're looking at. So we're honing our vision into this term. And so we're basically just pretending ln x is constant when we differentiate partially. So pretending x is constant, we have this. So this was the constant multiple, ln x in the denominator, and then differentiating x to the t, which is a to the t ln a, such that a is x, we get this. Okay, cool. Let's go ahead and just cancel out the ln x's in the same step and squish these together. Awesome. All right, so now we can kind of evaluate that integral on the right-hand side, and you'll see that it's 1 over t plus 1. All right. Now, what do we do from here? Well, recall how I said that this is the original integral at I of t equals 7. So what we'll do is now integrate my left and right-hand side. I'll write another line. Integrate on my left and right-hand side from 0 to 7 of I prime and t dt, and on my right-hand side, dt over t plus 1. And the purpose, like I said, is so that we can get this I of 7, because that is the quantity that we're trying to measure. That's our integral. It's a target integral. And this becomes ln 8. Okay, cool. So going ahead and moving this to the other side, we add it. So plus plus, and we get this equation for our target integral. Now, the problem is we don't know what I of 0 is. Looking at this, if we plug in t equals 0 here, 0 and 0, we get another integral that we don't know. So let's go ahead and write down what I of 0 is. I of 0 equals the integral from 0 to 1 of 2x cubed minus 2 over ln x with respect to x. Now, make an observation. If this exponent were to vary in the t world and t was being evaluated at 0, so t, and then we evaluated this at t equals 0, what would happen? Well, this would become 1, and we would have 2 minus 2. So then that integral at x equals 0, or t equals 0 in the exponent, would be 0. So that gives us a good indication that we can parameterize this quantity in terms of t. So we're doing a double Feynman technique, and that's what makes this so beautiful. The solution is so beautiful. And that's because we're doing Feynman's twice. So let's go ahead and differentiate under the integral partially. And I'm not going to bother with the partials. And this means that the derivative of I not t, our second parameterized integral, is going to be 2 over t plus 1. Okay, cool. So now what? Well, we'll do the same as we did before. And recall, we need the target integral. What is the target integral? Well, we put the parameter right here. So our target integral is 3, I sub 0 of 3. And also, if we plug in 0, we get 0. So that gives us a good indication that our lower limit should be 0. Our upper should be 3 of t equals the integral of 2 over t plus 1. And I forgot my differential. Okay, cool. This is going to give us our target integral. Our target integral, 3 not t, minus that 0 that we saw, so we can just leave it like that, is equal to, and I did not write our bounds here, 2 times what seems to be ln 4. All right, cool. So now we know what I sub naught of 3 is. Recall I sub naught of 3 was just I sub naught. So let's go ahead and replace I sub naught of 3 with I naught. And now we can make the substitution. So let's bring it back to orange, that the integral from 0 to 1 of x to the 7 plus 2x cubed minus 3 over ln x dx is equal to what we had originally, I believe, ln 8, plus what we just got to ln 4. And let's change that implies actually to a conclusion, because we're done here. And this is that beautiful double Feynman's technique to turn a non-elementary integral into something calculable. So, yeah.